I was muted. I'm not muted anymore. Um, when are we getting Duel of the Fates? Well, here's the problem with Duel of the Fates. It's that it's in the second worst Star Wars movie. RIP Episode 9. Congratulations, by the way, to Episode 1 for no longer being the worst Star Wars movie. But to that end, that's why we won't be doing Duel of the Fates. Anyway, I mean, it's alright to disagree. You're wrong. Episode 9 was atrocious. I literally laughed during a lot of the movie. It was so bad. It was a 3-hour long toy commercial with no reasonable connected plot. How are the cats? They're doing well. Um Honestly, episode 8 is not a terrible movie. It's a bad Star Wars movie, but it's not a terrible movie by itself. Episode 9 is just a bad movie. And I'm gonna this is the hill I'm gonna die on. Episode 9 is garbage. It's one of the worst movies I've seen in the last 3 years. And I've seen a lot of straight to Netflix movies. Anyway, today we're actually going to not just rant about Star Wars and 80s music. We are actually going to teach a class today, so I'll go ahead and get started here. So today we're going to be talking about recursive data structures as it relates to trees. So this builds off what we talked about with linked lists last time. I wouldn't watch the remake of the Fantastic Four unless the alternative were like losing body parts. And then I'd have to ask which body part. Left pinky? I can deal without. I can deal without. All right. So we actually teach computer science here. We don't just rant about movies. Oops, wrong button. Here we go. Just some quick announcements. Reminder, homework 5 is due tonight. As usual, you have the standard 2-day late policy. 10% per day. Do get that submitted. As a reminder, the automatic feedback only applies to the recursion problem. And so the concurrency part of the homework, you will not get automatic feedback on. As a note, and I just say this because I've seen the same question posted on Piazza about 30 times in the last 5 days. Do yourself a favor. This is not for my sake. I don't care. I don't have a life. I can type on Piazza all day if I want to. Do yourself a favor and search before posting, and here's why. If you are waiting on someone to reply, but your question has already been answered, it will help you out considerably to search before posting because you will find the answer faster than I will type it. So do take that into account. Homework 6, we were actually going to release homework 6 today, and it was going to be one assignment that dealt with linked lists and one assignment that dealt with heaps. We decided upon looking at the assignment that it was simply too large, that having two very disparate assignments in one, I think, was just going to cause confusion. So we decided to go with a much simpler assignment, simpler in terms of easier to set up. We are also scaling the assignment down considerably. The design of homework 6 is such that it can be completed really in less than a week, so that it can be completed in a week. Because instead, we're going to release it next Monday. It's going to do binary search trees, which we are covering next Monday. It will be due April 28th, which is the last day of class. And for the note, we only have, counting today, 5 classes left, and that counts the exam review. So today, intro to trees. Monday, it's going to be binary search trees. Wednesday, we're going to do traversals. Now, traversals will be on the homework, but traversals are actually a lot, they're a lot easier than binary search trees. Traversals are like, hey, can you copy this code from the slides? That's the traversals part of the homework. And then on next Friday, we're going to cover heaps, and then we'll have the exam review. So just be aware of that. Are there any questions about the announcements? There is one more lab. Yes, there is a lab next week. I can't remember if we're doing a lab the following week. If it is, it's exam review. There shouldn't be an assignment. I will try to get an answer for that and announce it next week. But there is definitely a lab next week. Is the exam still same time and day? Near as I can tell, yes. However, similar to exam 2, it is unlikely that we're going to tell you that you have a 3-hour window to do the exam. Realistically, we will probably tell you that you can do the exam anytime that day. What is a move? Sorry? I misunderstood. Anyway, any other questions? And I by the way, I say probable on the exam because we actually haven't talked about the final exam yet internally because we've been focused on the homeworks. All right. There will still be a quiz this weekend. Be aware of that. So with that, last time we talked about recursive data structures. We talked about linked lists, and technically we didn't use this. This would create what's called a doubly linked list, where you go forwards and backwards. You could apply that, but we're not really going to spend any time on it. I just want to refresh everyone with where we were. So remember that the idea is linked lists. We use reference pointers between nodes in order to maintain order. We keep track of the first node and sometimes the last node in order to evaluate everything. We have this node class, and that node class stores some element, some object T, and you can define it in a generic way as well. Although we didn't in class on on Wednesday, but broadly, just want to refresh, we've talked about linked data structures. The idea, again, of a linked data structure is it looks a bit like this. And I'm intentionally going to draw this in a particular way. I'm not going to draw it left to right. I'm going to kind of draw it diagonally downward. Is that every class contains a node. That node contains some value. Doesn't have to be a number. We're just using a number here. It has a next pointer, maybe to some other piece of information. It has a next pointer. And then this points to null. And this would be a linked list, and we would keep track of the head node. Now, I intentionally wrote it this way just to kind of illustrate... knocked the camera out of focus there. Do you decide if a linked list is first in, first out, or last in, first out? If you want a list to be a stack, you make it first in, last out. If you want a list to be a queue, you make it first in, first out. If you want your list to be a list, you don't do either. Remember, a list is an idea that doesn't require you to implement a queue or a stack. A list is just a means to implement a queue or a stack. Is a linked list an ADT? It's not an ADT because list is an ADT. So just a quick reminder, the idea that we have is we have this abstract idea of a list, and it's implemented specifically 2 different ways, although there's actually more, but that we've covered in this class. There is array list, and there is a linked list. And the way to think of this is that this is like a gas-powered car, a petroleum-powered car. So I'll just write gas. And this is like an electric car. And the point is, if you can drive an electric car, you can drive a gas-powered car. If you can drive a gas-powered car, you can drive an electric car. Why? Because the interface is the same. You have a steering wheel, gas pedal, brake pedal, etc. So list is an ADT. Array list and linked list are concrete implementations of that. A Tesla is just an electric guitar. Or electric car, not electric guitar. Sorry, a little bit of a stutter there. Anyway, So a linked list. Now keep in mind that there's two kinds of linked lists. There's the java.util.linked list, and that's exactly like array list. And then there's the linked list we built, which is our own custom linked list. But I don't want to spend too much time on that today. I just want to refresh us. This was where we were. So the goals for this unit are we're going to talk about data structures and more complex linked data structures, namely trees. And we are going to look at generic trees and binary trees, what the difference between those are. From there, we'll talk about tree traversals, binary heaps, and binary search trees. And specifically, we'll talk about binary search trees on Monday. So why does this matter? Again, the idea here is to think about data structure operations, the same that we did with a linked list, in order to, by understanding how the data structure is implemented, you can better appreciate when to use certain data structures, when they're strong, when they're weak, etc. So, what is a tree? Well, a tree is a composite hierarchical graph-like structure, and hierarchical is kind of a key word there. Composite just means it contains multiple elements. So a list is composite, but a list is not hierarchical. A list is ordered. With trees, we're going to talk about hierarchy, and the idea is we have predecessors and successors. Predecessors are parents, they go up. Successors are children, they go down. And so an illustration of a tree might be something like, I'm going to minimize this, but that doesn't mean being nice is any less important. A tree might look something like this. And if you think, wait, why does this tree start at the top and grow down? That's not how trees grow. Well, that's because computer scientists never go outside, and we didn't know that when we came up with the concept of trees. So, sorry about that. Anyway. The idea is, again, we have a series of nodes. These nodes have parents and they have children. And we have a few different kinds of nodes. So let's take this same idea and let's apply it to a drawing. So if I were to design a tree, that tree may look something like, say we have this 8 at the top. This is going to be my root node. The root node might have 2 children, might have more than 2 children, by the way, but it'll have, let's say in this case 2 children, might have less than 2 children as well. And the point of this tree is to organize data in some hierarchical sense. So 8 has 2 children, 5 and 3. 6 has no children, 2 has 1 child. So what I want to highlight here are just some definitional terms. The first is a leaf. A leaf is any node that has no children. No children. These are the ends. And the way that we model this in data, how do we model the end of a linked list? What does the next pointer point to? What does the next pointer point? Sorry, I'm trying to occasionally also keep in mind. Exactly, null. So technically these do have some kind of pointer pointing to null, to say there are no more children. However this is stored, we know null is somehow involved. Our root node is our node that has no parents, and exactly one root node will exist in a tree. The nature of a tree, because you can technically have multiple trees, but the nature of a tree is such that there is one root that everything descends from. The opposite of a leaf node is an interior node, and an interior node is any node that has children. So that's an interior node, that's an interior node, that's an interior node, and the root is also considered an interior node. It's a node that has children. This isn't related to inheritance. No, so we're not. Well, I mean, technically there are ways you could say this relates to inheritance when we get into things like sets and that, but not this graph structure. No, we're not talking about inheritance. Could the root node have more than 2 branches? Sure. There you go. The root node now has more than 2 branches. Also, that's a leaf node. This is a general tree, and in a general tree, we don't specify how many children each node has. Now, we will put a limit on that soon, but for now, to start with the basics, a tree doesn't require to have that. From there, another term to keep in mind. I'm going to pull the slides back up here. So we've talked about leaf, root. We've talked about an internal node. There's also a measure called degree. And the degree of a node is how many nodes or how many children the node has. So for example, my root has a degree of 3. My 5 node has a degree of 1. My 3 node has a degree of 3. My 10 node has a degree of 0. It's just the number of children. Now, again, I want to be very clear. This is a general tree. We're going to constrain this here in a bit. But this is the general structure of a tree. This is without putting any restrictions. Turns out this data structure is not particularly useful. Could you have 2 point to 1 or 8 to 1? So now you're asking a question. And the question is, could we have this path? And the answer is no, we're not allowed to have a path here from 2 to 1. And here's why. The nature of a tree is that everyone descends from the same root, and there is exactly one path from the root to any other node. So 1 has the path 8, 3, 1. If I were to add an edge here, there are now 2 paths. So in order to make this simple, in a tree, we add the stipulation that every node can only have one parent. Now, you can have graphs. You can have graphs where this node exists, but this would no longer be a tree. The nature of a tree is that every node has one parent. Or you can think of it as from the root to the node, there is only one path. Is there reason to account for the total number of... So we will constrain, in some particular cases, the number of children a node has. Very often we constrain that to 2. And it'll make sense, especially when we get to binary search tree, why we do that. Do nodes hold single elements? Correct. They only hold one piece of information. Now, that piece of information doesn't have to be a number. That piece of information could, in theory, be a string or a Pez dispenser or any object. For the sake of simplicity, I use numbers because they're easier to draw, and I'm a terrible artist. All right, so heading back to the slides here. The last word I want to mention is height. The height of a tree is the longest path from the root to the leaf. So let's find the height of this tree. So I should note that you can think of the height as different layers. For example, this is height 1. All of these 3 nodes. This is height 2. These nodes is height 3. And this node is at height 4. And the height of the tree is the farthest node, the height of the farthest node from the root. So because 9 is 4 steps away, the height of this tree is 4. So you think that you have caught me here, but I assure you, you have not. For you have been the one who's caught. Because, here's my question. Let's say I had 2 trees. Let's say I had 2 trees. This is tree number 1, and this is tree number 2. Tree number 1 has 1 node, tree number 2 has 0 nodes. What is the height of the tree with 0 nodes? It's 0. It's not -1, it's 0. Therefore, what is the height of the tree with 1 node? It's 1. Aha! I gotcha. Good try, though. I appreciate you actually trying to chime that in. Please don't, Bible Thump. That's why is that we specify the difference between a tree with no elements as 0 height versus a tree with 1 root as 1 height. That's the distinction we make. All right. The next thing I'll point out, and again, this is a tree with a height of 3, there's a difference between height and size. So the size of a tree should be null. Numbers can't be null. So we can't have a null int. So we also have the size of a tree. Now technically I deleted a node here, so I'm just going to put the node back. I think I had 1 in here. The size of the tree is the number of nodes it has. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9 nodes. So my size equals 9. And again, we start counting from 1 because size 1, size 0. Okay. So, what are some actual uses of trees? You might be thinking, like, why care? Well, your file system typically organizes files into a tree-like structure. For example, at root, you have C. That may have all the different folders. Let's say you have a folder for these 2 classes. That they have subfolders for the labs, etc. Further, taxonomy, animal taxonomies, that is going to often mimic a tree structure. Family trees, so actually I'm going to point out something. Family trees are not trees. And that's because most people have 2 parents. Knowing or otherwise, 2 people produce you. And as a result of that, technically you have more than 1 parent, and so therefore family trees technically aren't trees. I'm allowing for the possibility of bizarre situations or not, anyway. Well, I'm from anyway. I don't know. I'm not going to touch that with a 10-foot pole. Okay. Point being, so trees also serve a purpose in terms of coding. And they actually work well with recursive algorithms. So, let's take a minute and let's talk about some specific trees. So, we've already talked about a binary tree, but now I want to discuss, we already talked about a general tree. We haven't talked about a binary tree. I want to discuss the recursive nature of the tree. Consider the following. And I'm going to grab my blue marker if I can find it. I'll try the green marker. Green marker doesn't show up well, though, so apologies in advance. There's my blue marker. All right. So, consider that this is the root of this whole tree. But what about 3? What can you tell me about 3 relative to the tree I just outlined here? What is 3 in relation to this tree? It's a subtree, or 3 is the root of this subtree. See, this also behaves like a tree. And in fact, every node of the tree is the root of its own subtree. 5 is the root of a subtree. Even 6 is the root of a subtree. It's a subtree of size 1. So every tree is made up of subtrees, where every node is the root of its own subtree. And it turns out that this is actually something you've seen before, whether you're aware of it or not, with linked lists. With linked lists, and I'm going to erase this because I'm going to go to a binary tree anyway here in a second. With linked lists, the reason we call it a recursive data structure is because if you have a series of nodes like this whole thing is a linked list. But also, this part is a linked list, and this part is a linked list. Every node is the start of its own linked list. And so it allows you to write functions recursively based on this. Exactly. It is recursive in nature. It's what we mean when we say that a tree is a recursive data structure. Now from there, we're going to introduce a special restriction. And this is called a binary tree. And a binary tree has a limitation on the degree. That is to say that no node in the tree is allowed to have a degree larger than 2. Oh, sorry, if that bothering you? Rip camera angle. I know. I hadn't actually flipped it over yet. So we're going to add... Here, I'm going to erase the entire board because apparently not like this. I'm actually going to leave just that spot because I think it's funny. Anyway, I am a child. Anyway, from there, a binary tree may be set up something like this. Now, I want to be clear. I am saying the words binary tree. You may have heard the term binary search tree before. I am not doing a binary search tree, just a binary tree. So if you've heard that term before, you may be thinking something that I'm not going to do here. We will get into binary search tree. We just aren't there just yet. So I might have something like this. This would be a binary tree because no node has a degree of more than 2. And this actually allows us to design our tree based on nodes fairly effectively. Because technically, even though I only drew the nodes where they are there, I can... where'd my purple marker go? It's in my hand. Because we can also say that everywhere there is not a node, we're actually pointing to null. I'm going to have to actually wash this today because it's starting to get pretty dirty. Gotten a lot of use out of this, though. Worthwhile investment. So we have null everywhere that there is not a child. And so therefore we can define our node data type here as a node with 2 children. And I'm going to define these children in a fairly simple way. We have left and we have right. So this node contains a node for left and a node for right. It also contains some value. In this case, this is an int value, but again, this could technically be any data type. But the key is we have some left and some right. I'm just going to leave that 9 there the rest of class because I find it funny and I'm a terrible person. Anyway. So this is what we mean by a binary tree. I know, I'm childish. I really... Alright. I'm chaotic neutral. From there, we have this general tree description. Again, the general tree is not a binary tree. The general tree can have, in theory, n nodes. That is, n being any number. And it turns out we can define a lot of tree operations for a general tree without actually having to limit it to something like binary. So again, in a case of a binary tree, we would do something like this. This would be tree node E. And then you can differentiate between tree-wide operations and node-specific operations. What are the benefits of a binary tree over general tree? Because you have a much more predictable structure with a binary tree, you can do some things with it that you can't with a general tree, such as a binary search tree. It also makes the algorithms easier to predict. So, for example, with heaps, because our structure is tree-based, most of our operation, or binary tree-based, most of our operations will be log-based too, and very easy to write and recreate. Whereas if we have a broader tree, it doesn't actually improve the algorithm, and it makes the code harder to write. Once we actually get into some practical examples, it'll make more sense. So, for now, if we define a binary tree, the binary tree node is going to contain some piece of data, a left child, a right child. It could contain a pointer to parent. Just like when we have a doubly linked list, it contains a point to previous. You could just as easily say something like, yes, binary. Oh, yeah. Hang on. What are you talking about? There's no typo on this slide. Hang on. Wait. What are you talking about? There's no... Nope. Crap, I deleted the wrong letter. There's no typo on this slide. God. Sorry. I'll calm down today. The point being, we could... we could have a pointer back to the parent as well, where every node, and in this case, the parent pointer for the root would just be null. You don't need this pointer, it's optional, same as the previous pointer in a linked list, but you can have it. It wasn't a particularly sneaky move when I screwed it up 3 times. Anyway. So the idea then is we can have some node level operations. So, again, binary tree, we have roots, we have interior nodes, we have parent, we have children, we have leaf nodes. All those terms still apply. The degree is capped at 2, but as you can see on the whiteboard, we don't actually have to have 2 children. We just have to have 2 or less children. So, generally, common design, we'll skip over this part for now. Let's skip to how can we find the size of a tree? So we can find the size of a tree by finding the size of a node. And that may seem strange, but the idea is, remember, based on what we talked about before, why would you have a node point back to the parent? Same reason you would have a node in a linked list point to previous. You might need to be able to backtrack to perform some operations more quickly. We have... Remember, we have this overall tree where this node is the root, but we also have every node being its own subtree. So for example, 3 is the root of this subtree, and 5 is the root of this subtree. And so based on this, does it take more memory? Yes, it does. It takes more memory, so you only do it when you have a practical benefit. So based on this, I can actually define a size of a node. And the way I'm going to define the size of a node is the size of a node is 1 plus the size of its left tree and the size of its right tree. For example, this node 5, the size of the left tree, well, the left tree is null. So the size of null is 0. The size of the right tree is 0. 0 plus 0 plus 1 is 1, and that is an accurate portrayal of the size of this tree. Let's consider 7. The size of the left tree is 1, because there's only one element here. Size of the right tree is 1, so the size of this tree is, in this case, 3. And we can define this in a recursive way. Would you use leaves as your base case? That's exactly correct. Leaves are the base case, or specifically, actually beyond the leaves. So let's take a minute and let's actually just look at this code. So first we're going to say for the tree, if the root is null, return 0. Else return root.size. So notice this size method is not on the tree. This size method here is on the node, root. So now we need to look at the size method for the node. And what we're going to say is the initial size is 0. We're going to get the size of the left side, the size of the right side, and then size plus 1. Now the base case here is where a node is a leaf, because then this is 0, this is 0, and this is 1. So we might write this method like this. But notice we're recursing by calling, and again, left means the left node. We recurse here, left.size. We recurse here, right.size. We don't recurse when both of these are null. So yes, leaves in this case are the base case. So, based on this, let's do a full recursive find, and I'm going to use the blue marker for this. So let me erase any extraneous numbers here. I need to find the size of this whole tree. So the way I do it is first I need to find, starting from here, I need to find left.size. So now I'm here. How do I find the size of this tree? Left.size. I look here. There is no left, so left size is 0. There is no right, so right size is 0. I have to add 1, and so the size of this tree is 1. So I now know the size of my left tree up here, but I need to know the size of my right tree. Well, for the same reasons, the size of this tree is 1. So I have 1 and 1 plus 1, the size of this tree is 3. So now I have the size of the left tree for my root, but I need to find the size of my right tree. So, in order to find the size of the right, I need to search down here. There is no left tree, but there is a right tree, so I need to recurse further. There is a left tree, I recurse further. This is a leaf, so it has size 1. I recurse back up here. There is no right subtree, so 1 and 0. 1 plus 0 plus 1 is 2. 0, which is the left subtree, plus 2 plus 1 is 3. And so the size of my tree is 3 plus 3 plus 1 is 7. This is how we recurse. How would you iterate through all the subnodes if the tree isn't binary? You would need a loop, and then you'd have to store your nodes in some kind of collection like an array list, but the general algorithm wouldn't change. It just depends on how you store the nodes. So that's how we can do the size. Is like that. We can do the height, by the way, in the same way. So I want to clarify something. There are two size methods. This is the size method on a node, and we call this function on a node. This is not the size of the tree. This is the size of a node. The tree is the size of the root. Root.size. So we would call the first thing we would call is, we would say, okay, on this tree, I want the size of the tree. But in order to get the size of the tree, I call root.size. Because remember, just like linked list, there's actually two different classes here. There's the tree class and there's the node class. The tree contains nodes, but the tree and node are not the same thing. So in order to get the size of the tree, we simply get the size of the root node. We could do the same for height, etc. Any questions? All right. So from there, we'll pause here and we'll pick up on how would we structure this tree predictably on Monday. But I want to introduce the in-class activity first. So, it's pronounced height. It is not height. I know. I'm from West Virginia, and so I don't know how to speak English. It's an important caveat to note. So you're going to download the binary tree node class, and then in the main method, you are going to have nodes 1 through 8. You're going to use binary tree node integer, and you're going to just create your binary tree by adding all the nodes to B1. And the idea is you want to produce the tree in this image. So in order to do this, how do you turn the in-class in? It's an assignment in Colab. You should just upload your file. I think it's an assignment in Colab. Let me... oh, you can see my quick music hacks here as I just use YouTube. Like which files? Oh, you're just going to turn in you're just going to turn in the binary tree node because you're going to edit the main method. So all you need to do is do things like set left, set right. So I want to give you a head start here. We're going to cheat. We're going to give you all a little tip on how to get started. And you can pull up the assignment on your own screen to look at it while I quickly, there's my eraser, give you some hot tips, the inside scoop as it were. Oh no, I erased the 9. I said I wasn't going to do that. I have no stick-to-itiveness. Oh well. Yep, you're exactly right. Justice. Anyway, the idea is you're going to create, and by the way, I'm abbreviating binary tree node to just node. You're going to write binary tree node, but you're abbreviating node integer. Let's call this n1 equals new node 1. You're going to create nodes like this, and so you're going to have the same line for n2 equals new node 2. And then from there, if you want to make, and I'm just going to pull up the image real quick. If you want to make 2 the left child of 1, you would for now say b1.setLeft b2. So in this case, I used n, so n1.setLeft n2. Now I want to be clear. I want to be very, very clear about something. Just because I saw this problem before last year. So this was a problem a lot of people had. So with that, this is how you're creating node connections for the in-class activity and only the in-class activity today and Monday. You will not create node connections this way on the homework. So if you create node connections this way on the homework, you're actually going to have a lot of problems. This ended up causing a lot of confusion last year. So don't think you're going to do this on the homework. Because you won't. If you try to do this on the homework, it won't work correctly. The way you add nodes to the tree on the homework, which will come out Monday, I'll discuss, is just going to be to you call the insert method that you're going to write. So you won't ever directly connect nodes like this. Rather, you're going to rely on your insert method, which, again, will make more sense when you see the homework. My point is, do this on the in-class activity, and only the in-class activity today, and then there'll be a new one Monday. With that, happy to take any questions. Otherwise, the class will be over. What do you do with the created binary tree of type integer in step 2? I'm not sure what you mean. Do you mean this one? I'm not actually sure what you're asking. You need to create this tree. So you're going to have 8 nodes, and you need to create this tree where 1 is the root, 1 left is 2, 1 right is 3, 2 left is 4, 2 right is 5, etc. You're creating the tree in this image. I apologize that I'm not understanding the question if I'm missing it. I tried playing Modern Warfare on PC. I played 3 games. All of them had hackers. Like, I observed, and they were clearly aimbotting. They ended up with like 30 kills plus. So I I immediately uninstalled that because I already suck at shooters. I don't need hackers. It says create a new binary tree of type integer. So you're going to create a binary tree node for now. Remember that the nodes can be in a tree. I mean in Warzone. I don't actually own. I haven't bought Call of Duty. I haven't bought a Call of Duty game since Black Ops 3, and I never even played Black Ops 3. So yeah, I'm not. Will you take any homework 5 questions after class? I will not because I'm actually swamped today. So as soon as this class ends, I'm doing a meeting with my TAs in my other class, and I'm in meetings until 6 p.m. And after 6 p.m., I can finally get work done. So unfortunately, no, I will not be, but there are office hours today, and you can join those. Yeah, I know I haven't given you the '80s music reference today, but I do have a special surprise once I turn the stream off. Last chance for questions. Who should we talk to if we want a TA next year? So here's how we do that. We actually don't start hiring TAs until closer to the fall, and that's going to be especially true this year because without the on-campus or excuse me, I said the C word, my bad. Without the on-grounds presence, it's really difficult for us to vet candidates. So in the very very early fall, at the very beginning, yes, you do get paid to be a TA. I want to be clear, you do. At the very beginning, we will start hiring TAs for this class as well as for. So I'm not teaching 2110 next fall. I'm teaching 1110 and 3240, which you need to take 2150 to take. But we will be hiring TAs then. Any any last questions? All right. Well, with that, for the today's in-class activity, yes, you're going to manually add the nodes yourself. Are these slides up? They will be in the next 5 minutes. I was finishing them right before class, and so I will upload them here in the next 5 minutes. I didn't have any source code today, so there won't be any source code. But yeah, Stewart is in the bathroom. Yes, there he had to. There's actually not a cat litter pan in there. He just likes to go into the bathroom and stand on top of the toilet lid and rock it back and forth to annoy me. Because then I give him attention. And now he's sleeping on my shirt. All right. Take care, everyone. Have a great weekend. Best of luck finishing up homework 5. I will see everyone Monday with binary search trees. Take care.